Welcome back to the ChemDoctor, and this is the seventh video in the series on gases. And what we're going to do here is apply gas laws to the stoichiometry issue with a chemical reaction. And the problem at hand is that we've got 10 grams of propane that's going to react with an excess of oxygen to produce a theoretical yield of carbon dioxide and water. And in this particular problem, what we want to know is we want to calculate the volume of CO2 produced if when we run the reaction we collect the carbon dioxide gas that's produced at 1 atmosphere of pressure and 355 Kelvin absolute temperature. So basically we can break this problem down into two parts. In the first part, we want to handle the stoichiometry, the classic stoichiometry, all right, and this is going to involve two things. We need to find the moles of the propane that's going to react, and secondly we're going to need to use a mole ratio from the balanced equation to find the moles of CO2, moles CO2. All right, and then once we've accomplished that, once we know how many moles of CO2 that we find here, then in the second part we use PV is equal to nRT to calculate the volume of the gas that's formed. So number one, we need the moles of the CO2 produced. Number two, we're going to use PV is equal to nRT to find the volume. Okay, so I think this is a pretty straightforward problem. What we're going to do first is take the 10 grams of propane and we pull it down. We rewrite it, careful to keep our labels in here. We want to use good habits and unit multiplier method to carry the process out. So we're going to find the moles of this first, which means we're going to need the molar mass of propane, and to find that we need to recognize that there are 3 carbons. Each carbon is worth 12.01 grams per mole, and there's a total of 8 hydrogens, and on my periodic table my hydrogens are worth 1.008 grams per mole, and the grand total is going to be 44.1 grams per mole for the propane. So in this first step what we're going to do is essentially divide the 10 grams by 1 mole, the mass of 1 mole of propane. So the unit multiplier is going to look like this. And when we carry out the calculation, we're going to get about 0.2268 moles of the propane. All right. And I'm not being careful with significant figures. I think if you follow my my teaching videos, that you already know this. The main thing I'm concerned about here is that you actually know how to do the problems, and if you're in a particular chemistry class with a professor or a high school teacher, if you're at the high school level in AP chemistry or regular chem, you may have to be real careful with that stuff depending on the individual. Now, in the next step, we want to go to the CO2. So we're going to use a ratio from the balanced equation, and we see that for every mole of C3H8 that is combusted with the oxygen, that we produce 3 CO2s. So we're going to have 3 CO2 in the numerator here, or in the top of the mole ratio fraction, and we're going to have 1 mole of C3H8 in the bottom of the fraction. All right, and this is going to be this is going to be equal to about 0.6803 moles of carbon dioxide produced in the reaction. Keep in mind that we're in this problem, to keep life simple, we're ignoring the fact that there's H2O gas also being produced. We're just focusing in on the CO2 to keep life simple here. So this is essentially step number 1 that we've completed. All right, now step number 2, we're going to use PV is equal to nRT to find the volume of the gas. So first thing we're going to do is solve for the volume. We divide both sides by the pressure. So we're going to have nRT over P. All right, and now we can plug in the values that we have. All right, so for the moles of carbon dioxide, we have 0.6803 moles CO2. All right, and that's going to be times R, which is the gas constant, so 0.0821, and it's in units of liters atmospheres over mole times Kelvin. All right, the temperature is 355 Kelvin. Careful to put the units in all the way across here, and we're dividing by 1 atm of pressure. Now, you can see when you look closely at this that the proper units are canceling. We have moles canceling with moles. We have atmosphere canceling with atmosphere. We have Kelvin that is canceling with Kelvin. And we have successfully solved for the liters here. So I'll put my unit over here. Notice that I went through that whole thing with the units without doing any number crunching, because I want to be certain that I actually solve the equation properly for what I want. And since I want volume, well, then the unit liter better be over here. Otherwise, I've messed up somewhere. All right. Oh, okay. So what I get is 19.87 liters. All right. And so I think this is a pretty straightforward problem. So in the simplest form of gas stoichiometry problems, you're going to break the issue down into 2 basic steps. You're probably going to need to figure out how many moles of gas, of the particular gas that you're going to produce on the simplest level, and then you're going to use the ideal gas law to solve for the volume at the simplest level. All right, and with that, I'm going to go ahead and close the video.